You know, usually when we talk about collisions in the tech world, it's a bad thing, like a database collision or maybe a self-driving car failure.
Or just two CEOs realizing they can't stand each other.
Exactly. But today, we are looking at a collision that, well, it actually fixed a massive problem.
Yeah. This is the moment. Two totally different worlds. I mean, worlds that honestly didn't speak the same language kind of crashed into each other and created something, arguably better than either of them alone.
We're talking about the moment the transformer architecture, the thing that gave us ChatGPT and essentially solved natural language processing, was suddenly and surprisingly successfully taught to read images.
It's the story of how computer vision got swept up in the transformer revolution. It's really a unification story.
And to really get into the weeds of this, we have a stack of sources that are, well, they're heavy hitters. We're looking at a technical blog post from Meta AI introducing their DETR framework.
DTR, which stands for Detection Transformers.
Right. And we're pairing that with a lecture from the legendary Stanford CS231n course, specifically the module on detection, segmentation, and vision transformers.
So we have the industry breakthrough from Meta, and then the rigorous academic breakdown from Stanford.
It's the perfect mix. And our mission today is pretty specific. We want to figure out how we went from these really complex, handcrafted pipelines for spotting a cat in a photo to these elegant end-to-end systems that treat pixels essentially just like words in a sentence.
It sounds abstract, but it's actually really grounded. It's about finding one architecture that can basically do it all.
So let's unpack this. Before we get to the shiny new transformers, we have to understand the headache that came before them. If I'm an engineer 5 or 6 years ago, living in the era of, say, faster RCNN, and I want to build a system to detect objects, what am I dealing with?
Oh, you're dealing with a significant migraine. The pre-transformer landscape was effective, don't get me wrong. I mean, models like faster RCNN were the gold standard. But they weren't just one smooth neural network. They were more like a Rube Goldberg machine.
A pipeline of duct tape and heuristics?
A little bit, yeah. Ideally, you want to feed an image in and get cow out. But in the old way, the model couldn't just look at an image and say cow. It had to make guesses first. We relied heavily on something called anchor generation.
Anchor generation. That sounds like something you'd do on a boat.
I wish it were that simple. Think of it more like a template or a cookie cutter. The computer would just blindly place a bunch of boxes of different sizes and shapes all over the image.
So just throwing thousands of boxes at the image and seeing what sticks.
Tens of thousands sometimes.
Yeah.
It's just this brute force grid of guesses. And because you're throwing so many boxes, you end up with a huge mess. You might have 50 boxes all circling the same poor cow.
Okay, so now I have 50 detections for one cow. That seems useless.
It is.
Yeah.
So then you need another heuristic, another rule you wrote by hand called non-maximum suppression.
Which is just a fancy way of saying delete the duplicates.
It's basically a bouncer at a club. It looks at all the overlapping boxes, finds the one with the highest confidence score, the VIP, and kicks all the rest out.
Okay, but that sounds, it works, right? It sounds fine.
It works, but it's brittle.
Yeah.
It requires a ton of manual tuning. If your anchor boxes were the wrong size for what you were looking for, maybe you're looking for giraffes, but your boxes are all square, the model just fails. You're engineering the process, not just learning the result.
You're hard-coding your assumptions into the math.
Exactly. And that's never good for generalization.
Why?
So, meanwhile, while the vision people are, obsessively tuning their anchor box sizes, the NLP crowd is having a completely different party.
A full-blown revolution.
Totally. They've discovered the transformer, this architecture introduced around 2017 with that famous paper, Attention is All You Need, ditched all the complex loops they used to use and focused on one single mechanism: attention.
We hear this word constantly, self-attention, but I feel like people just nod along without actually knowing what it means.
It's simpler than it sounds. At its core, attention allows the model to look at a sequence, like a sentence, and for every single word, understand its relationship to every other word, all at the same time.
So it's context.
It's high-speed parallel context. If I say the bank of the river, the model knows bank relates to river, not money. It focuses its attention on the relevant connections. It doesn't read left to right. It reads everything at once.
But for a long time, computer vision was like, that's cool for you text guys, but we have pixels, not word. Our data is a grid.
Exactly. Vision hadn't been swept up, as the Meta researchers put it. But that's where DETR comes in. Meta AI decided to, bridge that gap. They released DTR detection transformers. And their goal was bold: Throw away the anchors, throw away the non-maximum suppression bouncer.
And create a truly end-to-end deep learning solution.
That was the dream.
So how does DETR actually work? Because images are 2D grids. How do you take a mechanism built for linear sentences and make it find a person in a photo?
Meta reframed the whole problem. Instead of guess a million boxes and filter them, they cast object detection as an image-to-set problem.
Image to set. That sounds cleaner.
It is. The model looks at the image and just predicts a fixed set or a list of all the objects present, all at once. It says, here's my list. A person, a surfboard, and a seagull.
And if there are no other objects in the scene?
Then it just predicts a no-object class for the remaining slots in the list. It's incredibly direct, no filtering needed.
But what's happening under the hood? Is it a pure transformer?
Not quite, not yet. DETR is a hybrid. They still use a standard CNN like a ResNet to extract the visual features from the image. That's the eye that sees the textures and shapes.
Got it.
But then they feed those features into a transformer encoder-decoder.
Okay, so the CNN sees the raw data, but the transformer does the thinking.
Precisely. And this is where it gets really, really cool. Because the transformer uses self-attention, it reasons about the image globally.
Global reasoning. This is the big aha moment the metablog talks about.
It is. In the old way, the model looked at a bounding box in isolation. It didn't really know what was happening 5 feet to the left. It had tunnel vision.
Right.
But DETR sees the whole picture. The meta source gives a fantastic example. Imagine a picture of a beach.
Okay, I'm picturing it.
There's a person standing there. Next to them is a partially blocked object. It's blurry, you can't really see it. An isolated model might look at those pixels and just guess blob or maybe umbrella.
Sure.
But DETR sees the person, sees the beach context, and uses attention to infer that the object next to the person is likely a surfboard.
Because it knows the relationship between person, beach, and surfboard.
Exactly. It attends to the relationships between objects, not just the pixel correlations. It's looking at the scene logic. If there's a beach and a person in a wetsuit, that blob is probably a board.
That feels so much closer to how humans see. We use context clues all the time.
Right. But there's a technical challenge here. You mentioned earlier that the old way had that delete duplicate step because it predicted 50 cows.
Yeah. What stops DETR from just spamming its list with surfboard, surfboard, surfboard?
That's the clever mathematical trick. They use something called bipartite matching.
Bipartite matching. Sounds like a dating app algorithm.
It's actually not far off. It's a one-to-one assignment problem. During training, the model forces exactly one prediction to match exactly one ground truth object. It uses a specific loss function, the Hungarian loss, that penalizes the model heavily if it tries to output duplicates.
So it's like musical chairs.
That is the perfect analogy. There is only one chair per object. The model has to learn to be decisive. It can't hedge its bets.
And the result of all this complexity reduction, the metablog says something about code size that honestly blew my mind.
It's wild. They claim that the inference code, the part that actually runs the detection, can be boiled down to just 50 lines of Python.
50 lines. Compared to the spaghetti code of the old pipelines, that is just incredibly elegant.
It democratized the architecture. It meant you didn't need to be a wizard of heuristics to build a detection model.
So DETR proved you could use transformers for detection finding where things are. But the Stanford lecture takes us a step further. It talks about using transformers for pure recognition. Just looking at an image and saying, that's a cat, with no CNN at all.
Right. No eyes, just brain. Yeah. This is the vision transformer, or VIT. And the title of the paper they reference is just perfect. An image is worth 16 by 16 words.
An image is worth 16 by 16 words. I love that. But how do you physically turn an image into words?
You literally chop it up. Imagine you have a photo of a cat, say 224 by 224 pixels. VIT breaks that image into fixed square patches, usually 16 by 16 pixels.
Like making a mosaic out of tiles.
Exactly.
Yeah.
And it takes each little square patch and flattens it into a long vector of numbers. It does a linear projection, basically compressing that patch into a code. And to the transformer, that code is treated exactly like a word embedding in a sentence.
So patch 1 is patch 2 is cat, patch 3 is sat.
In terms of the data structure, yeah. But there's a catch. In a sentence, order matters.
Yeah.
Man bites dog is very different from dog bites man.
Right.
But a bag of image patches doesn't inherently have an order. If you just feed them in, the transformer has no idea that the top left patch belongs in the top left. It just sees a pile of puzzle pieces.
That seems like a fatal flaw. You need to know the ear is above the neck.
It would be fatal. So they have to add something called positional embedding. They learn a specific vector that gets added to the patch data that essentially says, I belong at row 1, column 1, or I belong at row 10, column 5.
So you're digitally numbering the back of the puzzle pieces.
Yes. Without that, it's just a jumbled visual soup, but with it, it can reconstruct the spatial relationships.
Okay, so we have our patches, we know where they go, we feed them into the transformer, and unlike a CNN, every patch can look at every other patch immediately.
Yes. There is no masking. The top left corner patch can attend to the bottom right corner patch in the very first layer. This gives it that global reach right away.
But here's the part that confused me in the lecture notes. In NLP, you usually predict the next word. Here, we just want to say, cat. Where does that answer come from? Which patch has the answer?
That is a great question. Does the answer come from the ear patch? The tail patch? The answer is a quirky little hack called the classification token.
The class token.
They add a special extra input at the very start of the sequence. It's a learnable vector that doesn't correspond to any piece of the image. It's just a blank slate.
A placeholder.
Exactly. As the data flows through the layers, this token's only job is to gather information from all the other patches. It looks at the ear patch, the whiskers patch, the tail patch. By the end, that token holds the summary of the entire image.
That is bizarrely cool. It's like sending a reporter into a crowd of patches to interview them and come back with the headline.
That's a great analogy. And the most fascinating part, this architecture is identical to the one used in NLP models like BERT. It's the exact same math. We stopped building specialized eyes and just started feeding visual data into the brain we built for language.
That really drives home the unification theme. But, nothing in AI stays static. The Stanford lecture goes into some tweaks. It seems like getting these things to actually learn without crashing required some serious engineering.
Oh, stability is the name of the game.
Hmm.
Transformers are notoriously hard to train. The lecture highlights a few key evolutions that fix this. One major one is prenorm.
Prenorm.
In the original transformer, the normalization, which keeps the numbers stable, was placed after the main operations. It turns out that made it really hard for information to flow through deep networks.
So they just moved it.
They moved the normalization inside the residual connection before the attention mechanism. It's a tiny change, but it made training much, much more stable.
And then there's RMS norm.
Root mean square normalization. The concept is basically speed and simplicity. It's a faster, more efficient way to do normalization by stripping out some of the math.
Got it.
And then there's one more tweak mentioned that is absolutely critical for the massive models we see today, like GPT-4 or Gemini. It's called mixture of experts, or MOE.
I keep seeing this term, MOE. What is it?
It's a solution to a big problem. We want models to be huge, trillions of parameters. But running 1 trillion calculations for every single input is impossibly expensive.
Right, you'd burn through a data center in a minute.
So, Mixture of Experts says, let's break the brain into different specialized subnetworks, or experts. For any given input, a router decides which 2 or 3 experts are needed for the job.
So it's delegation.
Yes. Maybe for a patch of fur, it activates the texture expert and the color expert. For a patch of sky, it activates the gradient expert. You have a huge brain, but you only use a tiny percentage of it for any specific thought.
So you get the smarts of a giant model with the speed of a small one.
Precisely. The Stanford slides mention that almost all the state-of-the-art models today are using this MOE architecture. It's the only way to scale up economically.
It's efficient. Now, I want to zoom out a bit. We've talked about detection and recognition, but the Stanford lecture and the meta blog both touch on segmentation. This feels like the final boss of computer vision.
It is the fine-grained stuff. Detection gives you a box. Semantic segmentation gives you a label for every single pixel. This pixel is grass, this pixel is cow.
But semantic segmentation has a flaw, right? It's bad at counting.
Big problem. If you have 2 cows next to each other, semantic segmentation just sees a big blob of cow pixels. He doesn't know where cow A ends and cow B begins.
That seems like a problem if you're trying to build a self-driving car.
Huge problem. That's where instance segmentation comes in, which specifically separates them. And the holy grail is Panoptic segmentation, which DETR tackles.
Panoptic.
It unifies everything. It handles the things like cats and cars and the stuff like sky and grass in one unified framework.
And because DETR uses that global attention, it's remarkably good at this.
It is. Because it understands the scene as a whole, it can draw those boundaries much more naturally than the old approaches.
The meta blog brings up a really crucial point about why this all matters beyond just better bounding boxes. They talk about bimodal tasks.
Bimodal meaning 2 modes, text and vision.
Right. Because we're now using the same transformer architecture for both, it's much easier to build models that understand both simultaneously. They mention the hateful memes challenge.
Oh, right. Identifying memes. That's actually really hard for AI.
It's incredibly hard. You might have an image of a cute cat, which is visually positive, and you might have text that is harmless on its own, like, look at this mess.
Right.
But put that text over that image, add some cultural context.
And suddenly the meaning changes entirely. It could be sarcasm or it could be something negative.
Exactly. To understand that, you need a model that doesn't just process the image and the text separately. You need a model that can process the relationship between them.
And if both the vision part and the text part are speaking transformer, they can share information much more effectively. They can attend to each other.
It breaks down the silos between the research communities.
It really does. It suggests that the transformer revolution wasn't just about language. It was about discovering a fundamental way to process information.
That's a big claim.
I think it holds up. Whether it's a sentence, a sound wave, or a sunset, the mechanism of attention, of looking at the whole and identifying the relationships between the parts, seems to be a universal key.
It's a powerful idea. And before we go, I want to leave our listener with one final thought based on something you mentioned earlier about interpretability.
Right. Because DETR and VIT rely on attention, we can actually visualize what they're doing. We can look at the attention maps.
We can literally see which pixels the model is focusing on.
When it predicts surfboard, we can see it lighting up the person's feet on the beach. When it predicts zebra, we can see it tracing the outline of the animal.
So here's the question. If these models are analyzing the world by attending to relationships, like the person implying the surfboard, and we can see them doing it, are they starting to understand scenes in a way that looks suspiciously like human reasoning?
Or is it just really, really good pattern matching? That is the question that keeps researchers up at night. Are we simulating reasoning, or have we stumbled upon the mechanism of reasoning itself?
A bit of an existential cliffhanger for you there. We'll let you ponder the nature of machine understanding. Thanks for listening to this deep dive. See you next time.